Welcome back to The Explainer, everyone. Today, we're diving into one of the absolute wildest, most resilient sagas in the history of space exploration. I'm talking about the European Space Agency's ExoMars mission. And look, this isn't just your standard robot goes to space story. No, this is a masterclass in scientific ambition, international cooperation, and literally overcoming near-impossible roadblocks to uncover the secrets of our solar system. We've got a ton of fascinating ground to cover today, so let's just jump right in.
Was there ever life on Mars? I mean, that single, profound question is the entire driving force behind this multi-billion-euro endeavor. Now, you and I know that the spacecraft exploring Mars lately have shown us a surface that's pretty much just dry and barren today. But billions of years ago, it actually looked a lot like Earth. It had water flowing in rivers, lakes, maybe even vast seas. And if life ever took hold during that early wet period, well, the evidence is out there, just waiting to be found. Which brings us to the hero of our story.
Meet the Rosalind Franklin rover, appropriately named after the pioneering scientist who helped discover the structure of DNA. She is an absolute engineering marvel. This rover is destined to explore a very specific region called Oxyaplanum. Why there? Well, scientists believe this area might have actually been an ancient ocean sitting right at the boundary where channels from the southern highlands connect to the smooth northern lowlands. Basically, it's the perfect hunting ground for ancient biological secrets.
All right, Section 1, Searching for Martian Life.
Okay, let's dive into this. We're looking at the core of the Pasteur payload. These tools basically act together as a robotic scientist. First up, you have the PanCam positioned right up high on a mast. Think of it as the rover's eyes, using stereo and high-res imaging to scout the terrain. Then, down near the drill, there's Kloopy. This acts like a geologist's magnifying hand lens for getting those really close-up inspections of the soil. Now, before it even starts digging, the Wisdom radar sends ground-penetrating signals down to reveal any subsurface structures. And finally, the absolute crown jewel inside the rover is MoMA, the Mars Organic Molecule Analyzer. This uses mass spectrometry to literally sniff out the building blocks of life in crushed rock samples.
But, having the right tools is really only half the battle. You have to look in the right place. And that's exactly why this number right here, 2 meters, is absolutely vital. The Rosalind Franklin is uniquely capable of drilling a full 2 meters beneath the Martian surface. And this is totally critical because the surface of Mars is just constantly bombarded by harsh space radiation that totally destroys organic molecules. So by drilling down 2 meters, Rosalind Franklin completely bypasses that radiation zone. It gets to retrieve pristine, untouched soil samples that have basically been protected for billions of years.
Moving on to Section 2, Overcoming Mission Roadblocks. So this is a mission that was pushed to the absolute brink. I mean, originally, the European Space Agency was partnered up with the Russian space agency Roscosmos, and they were aiming for a 2022 launch. But in March 2022, ties were cut, and Roscosmos exited the mission. The rover was literally packed and ready to go, and suddenly, no lander, no rocket. It was a massive crisis. However, ESA member states totally rallied. They secured a €522 million lifeline contract with Thales Alenia Space to replace the missing parts. Fast forward to May 2024, a brand new global partnership was forged, getting the whole mission back on track for a late 2028 launch.
Let's take a look at how they built this new path forward. NASA really stepped up here with the ROSA project. That stands for the Rosalind Franklin Support and Augmentation Project. Basically, NASA is providing the SpaceX Falcon Heavy rocket, the crucial braking engines for the new landing platform, radioisotope heater units to actually keep the rover warm, and key parts of that MoMA instrument we just talked about. And right alongside this, Airbus won a £150 million contract to design the mechanical and propulsion systems for a completely new European landing platform. Honestly, it was just a spectacular rescue.
Which brings us to Section 3, Extreme Planetary Stress Tests.
Just look at this number for a second. 20 degrees. When you land on Mars, you simply cannot guarantee a flat surface. A large boulder, a treacherous crater, or even just a sudden gust of wind could literally jeopardize everything. So over at the Altec facilities in Turin, Italy, engineers built a full-scale replica of the landing platform. Then they deliberately dropped it onto a sled tilted at a steep 20-degree angle. Why? To simulate the absolute worst-case touchdown conditions you could possibly imagine.
And this brilliantly illustrates the sheer robustness of the new design. During these tests, they used a magnetic sledge to release the lander at varying speeds, slamming it into that tilted platform at up to 4 meters per second. And guess what? In every single test, the 4 legs of the descent module successfully absorbed that massive impact. But actually, what's more important is that it proved that touchdown sensors inside those legs could instantly trigger the engine shutdown. Because, think about it, if those sensors are even a fraction of a second too slow, the rocket plumes could blast Martian soil straight back up, overturning and totally destroying the spacecraft. No way we want that.
The sheer scale of this testing gauntlet literally reads like an epic movie training montage. I mean, beyond the drop tests, they took a dummy vehicle 29 kilometers up into the sky over Kiruna, Sweden, hanging from a helium balloon, and just dropped it to test the supersonic parachute deployments. Meanwhile, structural models of the rover were shipped over to Cannes, France, strapped to these massive shaker tables for extreme vibration testing, and then blasted with intense sound pressure in acoustic chambers. All of that just to simulate the violent roar of a rocket liftoff. They are leaving absolutely nothing to chance here.
All right, let's jump to Section 4, Protecting the Red Planet.
Listen to this rather stark warning from Albert Haldeman, ESA's Mars chief engineer. He said, if the rover were to bring life from Earth, we could get a positive signal that would be of our own making. So the crucial point here is this: we are sending a highly sensitive laboratory all the way to Mars to find alien life. The absolute worst thing we could do is accidentally bring Earth bacteria with us, test it, and then announce to the world we found life on Mars, only to realize it was just a microscopic hitchhiker from a clean room in Italy. A false positive like that would literally ruin the entire scientific purpose of the mission.
Because of that terrifying risk, international space law requires some incredibly strict planetary protection. And while that sounds wildly complex, and it actually accounts for just 5% of the total mission costs. Experts point out that this is highly comparable to what commercial airlines spend just to ensure passenger safety. So it's not a showstopper by any means. It's really just the cost of doing robust, reliable science. To really understand just how strict this is, consider our normal Earth environment. It's absolutely teeming with billions of microbes everywhere. But for the assembly of the rover's analytical laboratory drawer, the part that actually touches the Martian soil, the bioburden limit was set to a staggering 0.03 bacterial spores per square meter. I mean, to put that into perspective, that is the exact same level of sterilization required in a highly controlled hospital operating theater or a pharmaceutical drug manufacturing line. It is incredibly clean.
And the crazy thing is, it doesn't stop at the rover. Even the massive 74-kilogram parachute that slows the descent has to be completely sterilized using a process called dry heat microbial reduction. It starts with this 50-hour preheating phase, followed by a grueling 36-hour bake in a giant oven at 125 degrees Celsius. That's just to make absolute sure the heat penetrates the innermost folds of the fabric. Only after all that is it cooled down, wrapped in protective packaging, and shipped off for integration.
Okay, Section 5, the road to 2028.
So here is the final countdown. In late 2028, that Falcon Heavy is going to ignite, sending Rosalind Franklin on a long 25-month interplanetary journey to Mars. But the most terrifying part of the whole shebang is right at the very end. It takes approximately 6 minutes to descend from orbit down to the Martian surface. But because it takes radio signals much longer than that to travel between Earth and Mars, mission controllers literally cannot intervene. That entire 6-minute landing sequence must unfold completely autonomously. The spacecraft is 100% on its own.
But if it survives that terrifying descent, it will be an absolutely historic triumph. A successful touchdown won't just unlock the biological mysteries of oxyoplanum, it's going to permanently cement the European Space Agency's place in a very small, elite club of space agencies that are actually capable of achieving a soft landing on another world. Honestly, it's the ultimate payoff for over a decade of resilience.
Which leaves us with this final thrilling thought to chew on. After surviving geopolitical collapse, extreme drop tests, and a 25-month voyage through the absolute void of space, when Rosalind Franklin finally extends her drill 2 meters into the Martian soil in 2030, what earth-shattering secrets will we uncover? Will we finally answer the ultimate question of whether we're alone in the universe? Thank you so much for joining me on this explainer. I really hope you're as pumped for 2030 as I am. Keep learning, stay focused, and I'll catch you in the next one.